This chapter covers concepts that appear in almost every programming language and how they work in Rust. Many programming languages have much in common at their core. This is true. None of the concepts presented in this chapter are unique to Rust, but we'll discuss them in the context of Rust and explain the conventions around using them. Specifically, you will learn about variables, basic types, um, sorry, specifically, you will learn about variables, basic types, functions, comments, and control flow. So this is the bread and butter of programming, the high-level concepts. These foundations will be in every Rust program, and learning them early will give a strong core to start from. Okay, keywords. The Rust language has a set of keywords that are reserved for use by the language only, much as in other languages. Keep in mind that you cannot use these words as names of variables or functions. Most of the keywords have special meanings, and you will be using them to do various tasks in your Rust programs. A few have no current functionality associated with them, but have been reserved for functionality that might be added to Rust in the future. You can find the list of the keywords in Appendix A. So let's check them. Define constant items, or for this const. So all of these, so here, this is present in Python. Async and await. It's for concurrency using the same thread. Break it's for loops. Const, continue. Here, these two are maybe what's in the set theory. Set theory, the one complements the other. I I learned set theory in a different language than English, so I did not remember the exact saying. This is unique to Rust. Here, this is also, I think, unique to Rust. It's the grades are the library. That's what I've uh, I figure out. Okay. Let's continue. Variables and mutability. 3.1. So after I read chapter 3, before starting chapter 4, I will solve the exercises that are available. And the third option back here at the um, introduction. Okay, as mentioned in the storing values with variable section, this section was from chapter 2. If you check out the link at the bottom left of the screen, it's for chapter 2. But it was very, you didn't miss anything, essentially. As mentioned in this section, by default variables are immutable. This is one of many nudges Rust gives you to write your code in a way that takes advantage of the safety and easy concurrency that Rust offers. However, you still have the option to make your variables mutable. If you have worked with Prolog, in Prolog you cannot change the value of a variable. If you want for some reason to to make, to construct, to make, to allocate a value, to mutate the value of a variable, you you define a new variable that has the mutated value that you would like to store in the immutable. So essentially the same like let's say 3.1, 331 here, 3.01 dot rust. It's rs, the extension of the programs written in rust. So x equals 5, and if you want to change the value of x, because you cannot do that, you cannot change the value, you define a new one that is y is x plus 5. So if we want, if we, in Prolog, if we want to set the value of x to 10, we cannot change it, but we can define a new variable that is 10. So essentially, that's what it reminds me here, this contract, that the semantics of the of Rust, the point it makes. Let's explore how and why Rust encourages you to favor mutability, and why sometimes you might want to opt out. When a variable is mutable, once a value is bound to a name, you can't change that value. To illustrate this, generate a new project called variables in your project directory by using cargo new variables. We will go through cargo as well, but I don't want to get lost inside the tooling provided by Rust. I've read that cargo is an excellent a way to manage your crates. The cargo consists of crates. It's a beautiful way to correct selection of words to convey the semantic meaning of what the cargo is, and the crates that constitute the cargo. So the cargo brings in the crates to which a new project depends on. That's what cargo is. It's to install the dependencies, but we do not work with dependencies right now, so we will use it later. Let's get focused onto Rust. Then in your new variables directory, open src from the sources directory containing the sources of the project, main rs, and replace its code with the following code, which won't compile just yet. So we want to write this here. X is 5, and then print x. So we print 5 and change its value, which is incorrect in Rust, inconsistent with its rule set, and then print x again, which would be 6. Okay, save and run the program. You should receive an error message regarding an immutability error as shown in this output. So when we run, I will run my code in a different way. So fn, let's copy this, paste, and save. So I will do this rust compile. So I want to stay as minimal as possible when using stuff. when using tools, when using anything, because I want to be explicit. I want to have a clear goal of what I'm trying to achieve, and constraints always provide direction, what I'm going to do. So I will stick with the compiler for the time being and compile this here. So the error is the same as the one provided by the documentation by the book. So instead of cargo run, I just run the compiler, and this line is missing in our, but it's for the user. This line is for the user to understand what's happening, but we know what's happening, so it's redundant. Let's check. Let's the remaining of the error is the same exact thing, if you can see. Yeah, this also is missing here. This thing here, but this also is not present. But all of these differences are not important to us, to learning Rust, for sure. Okay, so the first the error is cannot assign twice to immutable variable x. The error number of this is 384. When you're trying this error is this number is the same thing when you attempt to assign a value to a variable a second time. Cannot assign twice to immutable variables. So in line 6, we try to do this, and in 3, line 3, obviously provided for context, we did print the x, and help is provided to us by the compiler. It says consider making this binding mutable. Okay, this example shows how the compiler helps you find errors in your programs. Compiler errors can be frustrating, but really, they only mean your program isn't safely doing what you want to do it yet. Yeah, not exactly. They are not doing it safely. The text does not obey the rules by the parser of the language. It's just that Rust wants to do things safely, and yeah, they do not mean that you're not a good programmer. Experienced stations still get compiler errors. Well, obviously, if you don't get compiler errors, that's that is problem. You know, no one writes clean code in the first iteration. You receive the error message because you try to assign a second value to the immutable x variable. It's important to get compile time errors when we attempt to change a value that's designated as immutable, because this very situation can lead to bugs. If one part of our code operates on the assumption that a value will never change, another part of our code changes that value, it's possible that the first part of the code won't do what it was designed to do. Rust, by the way, is designed for safety and concurrency. So this is a contract provided by the the grammar of the language, the parser, to not introduce race conditions, to help the programmer inhibit the human error, to prevent human error by by the default mutability for new variables to be immutable. Um, because of this kind of bug can be difficult to track down after the fact, especially when the second piece of code changes the value only sometimes. Yeah, because we will not be able to reproduce the bug consistently. The REST compiler guarantees that when you state that the value won't change, it really won't change. So you don't have to keep track of it yourself. Your code is thus easier to reason through. Yeah, as I said, when there are constraints, it's it's more clear what you're trying to do. We are trying to learn Rust, so I just use the compiler only. Your code is okay. So mutability can be very useful and can make code more convenient to write. Although variables are immutable by default, you can only make them mutable by adding mute in front of the variable name as you did in chapter 2. Adding mute for mutable also conveys intent to future readers of the code by indicating that other parts of the code will be changing this variable's value. For example, let's change here the and add mute. Yeah, this should then compile. So let's do it ourselves. It's also the boring part of learning. That's the most helpful, I find. So mute here to flag X as mutable, and then compile, and it compiles cleanly, and then I think the default executable given a source file is the name of the base name of the file, meaning without the extension of it. So this here. The value is 5, then the value is 6, which is correct. That's what we are doing. It aligns with our intent. We are allowed to change the value bound to x from 5 to 6 when mute is used. Ultimately, deciding whether to use mutability or not is up to you and depends on what you think is clearest in that particular situation. Yeah, I think that using immutable variables, to try to use only immutable variables, is the way to go. And be very careful with the mutable ones. Okay, so like immutable variables, okay, there's declaring constants, the second part of this sub chapter of chapter 3. So, like immutable variables, constants are values that are bound to a name and are not allowed to change, but there are a few differences between constants and variables. First, you aren't allowed to use mute with constants. Constants aren't just immutable by default, they're always immutable. You declare constants using the const keyword instead of the let keyword, and the type of the value must be annotated. Oh, yeah, the type of the value. Yeah, so Rust has a mechanism which can infer the type of a variable. So here in our code, this example that we didn't declare the value of x. The value of x could be um, unsigned int or signed int or float. We can we can also explicitly declare a type, but const constants are uh, it's mandatory for us to declare the type. We'll cover types and type annotations in the next section, the 3.2 data types. So don't worry about details right now. Just know that you must always annotate the type. So the difference is, so let's build this this out. Um, let's use a constant. Let's flash this example here. Each example will contain everything that each section is the information that it is conveying. So that, here's the mutable and unmutable stuff. So how's the comments? This is the comment. Use mute to, yeah, that's boring. Let's just use const x1 different, let's say y, const y of type unsigned of 4 bytes, unsigned date 4 bytes with value 5. Okay, and print this. Whoop, y here and y here. And compile. Great. So we got an error. Constants should have an uppercase name, and it's a warning. It's not an error. So still the program compiled, but we have a warning now. Let's change this from 5 to 20 or something else, because here x is also 5, and this can okay. Constants can be declared in any scope, including the global scope, which makes them useful for values that many parts of the code need to know about. The last difference is that constants may be set only to a constant expression, not a result of a value that could only be computed at runtime. Great, okay. A constant's name is, and its value is set to the result of multiplying 60 by 60 by 3. Okay, so it's a value. Rust's naming convention for constants is to use all uppercase with underscores between words. Compiler is able to evaluate a limited set of operations at compile time, which let us choose to write out this value in a way that's easier to understand and verify, rather than setting this constant the value. Okay. See the Rust reference on constant evaluation for more information on what operations can be used when declaring constants. Okay, so we will also briefly visit this. This is the reference. So this is the reference. Constants are valid for the entire time of a program runs within the scope in which they were declared. This property makes constants useful for values in your application domain that multiple parts of the program might need to know about. such as the maximum number of points any player of a game is allowed to earn or the speed of light. Naming hard-coded values used throughout your program. Yeah, naming is useful in conveying the meaning of that value to a future maintainer of the code, to future maintainers of the code. It also helps to have only one place in your code that you would need to change if the hard-coded value needed to be updated in the future. Okay, so we've covered the declaring constants, the constants part, and the variables in mutability. Let's get to shadowing, and that's the end of 3.1 section. As you saw in the guessing game tutorial in chapter 2, you can declare a new variable with the same name as the previous variable. Rust stations say that the first variable is shadowed by the second, which means that the second variable is what the compiler will see when you use the name of the variable. In effect, the second variable overshadows the first, taking any uses of the variable name to itself, rather until either it itself is shadow or the scope ends. We can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. X is 5 and then X is 6. And then X is 12, I would believe, and then print 12 and then print here 6. This is 6. 12 and 6 should be the two printed. This program first binds X to a value of 5. Then it creates a new variable, X, by repeating X equals, taking the original value and adding 1 to the value of X. So the value of X is 6. Then, within an inner scope created with the curly brackets, the third let statement also shadows X and creates a new variable multiplying the previous value by 2 to give X a value of 12. When that scope is over, the inner shadowing ends and X returns to being 6. When we run this program, it will output the following. 12 and then 6, as I assumed would happen. Shadowing is different from marking a variable as mute, because we will get a compile time error if we accidentally try to reassign to this variable without using the let keyword. By using let, we can perform a few transformations on a value, but have the variable to be immutable after those transformations have completed. The other difference between mute and shadowing is that because we're effectively creating a new variable, when we use the let keyword again, we can change the type of the value but reuse the same name. For example, say our program asks a user to show how many spaces they want between some text by inputting the number, the space characters, and then we want to store that input as a number. Okay, so here is the spaces as a string, a string literal, and then spaces as the number. This is a number here. The first is a string type, and the second spaces variable is a number type. Shadowing thus spares us from having to come up with different names, such as spaces str, and spaces none. Instead, we can reuse the simpler spaces name. However, if we try to use mute for this, as on here, we'll get a compile time error. Yeah, this is correct, because this space here is a string, whereas this here is a number. We rather we try to assign, we attempt here to assign a number. This is the number, the length of this string, and attempt to assign a number to a variable of type string. There says that we are not allowed to mutate a variable's type. Now that we have explored how variables work, let's look at more data types they can have. Okay, so some questions I have is, can I shadow a variable using a constant? Can I have a variable in the global scope is the second question. That's the two questions. And then another question is, no, I think that's the questions I have. A note is that all this details around immutable and mutable variables, and the default being unmutable, and the shadowing that is available. All of this, this group of ideas. That's I think it's not because the compiler can apply further optimizations, but rather I would say that it is to protect the programmer from human error. Possibly it helps to then build on top of this mutability and immutability and the shadowing and all this stuff, to build optimizations on top of those, but they themselves are not for optimizing the code. It's not semantics to have so that the compiler can have a contract, so it can optimize the generated the compiled code. Okay. So a third question is, which backend does Rust use? Is Rust using LLVM? LLVM? LLM? No. LLM is the large language models in AI. LLVM is the suite of compiler, the backend for compiling, and yeah, it's the compiler. Okay, the project rather.